I want to turn now to consider what happens in a cyclic process. Now, we've already stated that state functions have the particular property that it doesn't really matter what path they take to go from one point to another. So for a state function, I might have 2 points, and I'll draw them here, point 1 and point 2. And when a system is going to evolve from point 1 to point 2, it might follow a path like this. It might follow a path that's more direct like this, or it might follow a path like this. It really doesn't matter, though, which path it took. If I've got a state function, I'll use delta E as a generic state function, then simply the change in that delta E is just going to be the difference between its value at each of those points. And this is regardless of the path. So we don't have to worry about which path is followed by the system in doing this. All we have to do is make sure that we are making, in fact, a complete traversal from point 1 to point 2. Now, it's useful to know that for state functions, these include entities, many of the ones that we've talked about. They include things like the internal energy, they include volume, pressure, temperature, enthalpy. All of these would have this quality of not having to depend upon the path to get from one thing to another. And of these, we also have energy quantities that would include in this. So that would be things like, obviously, U and H, which those are state functions specifically of energy, but also products like PV or products like RT, which are energy functions that also are going to be state functions no matter what and not dependent upon the path. Now, let's suppose that in going between 2 points, and again I'm going to draw point 1 over here and point 2 over here. Let's suppose we have a path that goes, through some tortuous path on the way from point 1 to point 2. I'm going to call this path A. All right, and I'm going to say that the change in the internal energy for path A is just going to be U2 minus U1. So this is for path A. Now let's suppose that I follow a path B that goes from point 2 to point 1. So maybe it goes something like that. This is path B. All right, so it's moving along like this. So if I look at the internal energy for path B, that one's going to be expressed as U1 minus U2. So the interesting thing is if I go on path A and I follow that with a system that evolves along path B, now I'm going to have a total internal energy change that's just going to be the sum of the 2 internal energy changes. But I've already seen that this first one is just equal to U2 minus U1, and the second one is U1 minus U2. So when I add these together, it's going to equal 0. This is generally true of cyclic paths. So for a cyclic path, in this, and this includes delta internal energy, delta enthalpy, it also includes things like delta PV and delta RV, that all of these, or RT, all of these are going to be equal to 0 around a cyclic path. So this is true in general of all state functions. If you follow a cyclic path, their net change is going to be 0 because you've gone back to the same state that you started in. And another way that we write this sometimes, especially if you're adventurous mathematically, is we might write this as a cyclic integral. And the integral is written like this. It's an integral sign with a circle on it. And so, for example, an integral sign with a circle on it over a state function is always going to be equal to 0. And you can think of this as a mathematical proof, if you will, that something is a state function. Now this particular property is not true of non-state functions. So this would not be true of work or of, for example, something like like heat. Now, how might we address that? Well, let's suppose that I have a cyclic process in a PV diagram, and I'm going to draw it as a very simple cyclic process. So this is just a cycle that goes around in a rectangle. So it's going to go this way, and this way on these 4 points. Now, if I'm going along this path, what is the work associated with that path? Well, remember, it's going from left to right, so it's going to be a negative quantity, but the magnitude of that quantity is going to be the area underneath that curve. Okay, now I'm going to come down on this vertical path here, and that has no work associated with it because it's a constant volume path. Now I'm going to go across here, and this right to left path is now going to be a positive work contribution, but it's at a lower level. So in fact, the work that it describes is just this area. So I'm going to have negative work up here. I'm going to have positive work down here. They're going to cancel each other out down here where we've got the cross hatching. And so then I have a final step that's going to go up here back to the initial point that has again no work because it has no volume change. So in effect, what we're going to end up with, and I'll draw the sum of this over here, is we're going to have a process that went around in a cycle, and the total work done in that cycle is simply the area inside this box. So it's not going to involve the stuff below the box at all. And this is generally true of a cyclic process. So a cyclic process is going to have work has the magnitude of the area inside the cycle. Now, one of the things we got to be careful about is that work a positive work for the system or a negative work? Now notice in the case that I drew originally, we were going around the box, we were going around the cycle in a clockwise direction. And when we go clockwise in a cycle with work, then the work is going to be, the bigger contribution to work is going to be on the upper side, and the smaller contribution to the work is going to be on the lower side. But the upper side is going left to right, so it's negative. So the overall work in this case is going to be negative when the cycle is clockwise. If it's counterclockwise, it'll be the opposite is true. There, the higher level is going to be positive work, and the lower level will be negative work. So in that case, the total work for the cycle is going to be greater than 0. Now, you'll also notice that for these cyclic processes, I had delta U is equal to 0 for cyclic process. But I've just shown that the work, analyzed as the area underneath the curve, is not 0. So what this means is that since delta U is equal to Q plus W, and work is not 0, Q must equal negative work. So for heat, in this case, if I undergo a cyclic process, if the cyclic process is clockwise, then the heat is the opposite sign of work, so the heat will be positive. So the system should get hotter. If it's counterclockwise, then we should see that the heat would be negative. Sorry, Q is less than 0. All right, so I hope this gives you a feeling for these cyclic processes. It's a good thing to keep in mind because if you can always set in a cyclic process a state function as having 0 change, it helps you to evaluate a lot of things about the system.